Hello. I wanted to show off a project I've been working on. Right now it's mostly being held in Digital Logic Sim, which is a logic sim made by Sebastian Lake. So I think it's amazing and it's on itch. But I've been working on an 8-bit computer here. This is the computer itself that I've been working on. At this point it is entirely finished, and the only thing I will be working on for it is just programming it. But I wanted to show how I made it and what I've learned from it, and then ideally I'll take what I've learned from it and end up making a physical computer kind of similar to Ben Eater's breadboard computer, something like that, hopefully. And I want to put it on my own PCB, something like that. That'd be amazing to do. But for now we have this, and I can load up a simple program. I have a few lists of them. Let's see here. I also have my own assembler compiler that I programmed, well, with some help, but I'll show that in a second here too. Okay, so a few things that we can do here. This is a mostly CISC-based system, and unfortunately this Logic Sim is unable to have a very high clock speed. There's about 100 steps per second, but it's also running 6 steps per clock tick, so realistically that's under 100 hertz, which is, again, isn't great. It's not going to be able to be playing anything 3D on this soon, but it does have a display and a full ALU system, full branching logic and everything. And there's I'll show the opcode more in a little bit here, but it does rely on both 1-byte and 2-byte instructions, although it is all 8-bit, mostly for even the addresses. A few things you can do. Here, I'll copy some programs over. Obviously the program's going here. This is a raw module. This one's just outputting the Fibonacci sequence. It's nothing amazing. You can see it's happening here. I should probably put this to a display, but that one runs pretty quickly, obviously. Another thing you can do, let's see here. This will just kind of fill the screen with noise to see that the screen works. And here's where you really notice the low clock speed when it's trying to render full screen. After doing some calculations, if you're trying to render from VRAM entirely, it'd take about 1.1 FPS, which is amazing for a simulator I'm running at nearly 2000. I don't want to run that whole thing, it'll take too long, but a lot quicker if you just want to do a solid color. Determines the color here. I'll do, it should be red. Yeah. The fill command's in actually its own thing, so it doesn't require too many instructions to do. It actually only requires one just to fill the screen itself. Very nice. My next goal is to program Snake, and we'll see how that works. But I want to show you my visualizer and compiler that I made for it. So here's that. It's just a little React app. But so the few things it can do is it will let you visualize what command each binary thing can do. And then it also lets you write from my own assembly language that I made. So obviously we have a register file which has 6 registers in it. Additionally, we have RAM. It only holds 256 bytes. That's purely due to clock speed. Next, you did make a 64 kilobyte RAM. It's not in the save, but it lowered the clock speed to below 1 hertz, so I couldn't really use it. And then I'd have to copy that for VRAM if that'd be meaningful. So there's also for destinations. We have an LSFR, which is basically just a random number generator. You can see when you allow a clock, it'll come up with certain random numbers while the clock's running, that is. The IO register, this is for inputting different, it's for keyboard input. I don't know, I'm tracking a few keys right now. I'm kind of implementing it for Snake, but it does work. So, knowing that, let's look here. So I have 3 main modes. There's data movement, control, and ALU operations. So 0 will always be just no operation or break if you need to. 1 kind of is ALU. So any ALU commands or computational commands are usually 2 bytes. So in the first byte you'll have a source register, 2 source registers, different by 3 bytes, and it'll show you here. So 2 sources will be destination, you'll see it in a second here. So obviously 0 will be register 0, do 1, 2, all the way up, and then you'll have RAM, and then 111 will be input or output depending on whether it's a source or destination. So you can do input and RAM, and then do some operation on there. You'll see here. So the next byte, first 3 bits will be determining the destination. So you can do out, and then next 4 bytes determine the operation. You can do a lot of things. I'll show you them all here, but so yeah, only one's not really used right now. You can pretty much do whatever you want. We'll just do an add or something. And then write flags. It's actually a little broken in the code right now, but if this is on, it'll write the flags out. If not, it won't, but that's on by default when you're coding in assembly. And then 10 is movement. It's a 1 byte command. It's pretty simple. Just move, and then the next 6 bytes are just determining where from and where to. So you can do just move input to output. Pretty simple. RAM to register 4. And then after that you have control. There's a few modes in control itself. There is immediates, which are 2 byte things. So for immediate, these 2 will always be 0. And these 3 will determine the destination to where you're going to put that immediate to. So for example, RAM, which the address for RAM is being determined by register 4. So it's just kind of hard coded there. It's not the most ideal, but it works for lower clock speeds, and it's honestly pretty efficient for how I want to write my programs here. And then byte 2 is just a value to immediate. I did that so you're able to immediate up to 255 instead of, it'd be 63 if it was 1 byte. If you want to get a number higher than 63, it takes several clock ticks to get up to 255 or something. But this is nice, 2 bytes, and then you can get whatever number you want wherever you like it. Control, you can also do branch conditioning, which will be, so register 4 determines the line to branch to. Earlier I think I said that register 4 determines the RAM address. That's actually wrong. It's register 5. Register 4 holds where you'd branch to for loops or anything like that. And the next 4 bytes are just determining the operation to branch. So you're checking never, always, various different conditions just based off the flags. And again, you can write the flags to a register and saves it, and checking those flags to determine all of these things. So you can do a operation, and if you can even do more operations without writing the flags, and then much later check the operation from way back. Yeah. So then there's that, and then another thing there's some control things here. So this is mostly for display logic, and I also had somewhere else to move like VRAM control and IO control. So I kind of put that here. Not the most neat, but it does work. See, this is just moving VRAM wherever you'd like it to. Yeah. And then other than that, there's this one, which is moving IO somewhere. And then here, there's a few display commands. This is refreshing the display. This will toggle the writing on the display, fill the screen, reset it. And then this is pulling from the LSFR, which is just determining random number. Other than that, we have some more space for more options, but it's a quick breakdown of everything. Kind of put everything here. You got your notes here, they save in local storage, not too crazy, but. And then again, the assembler, it's pretty simple. I just have a basic thing like, if you want to, M's for immediate, do that, I don't know. So it does have some aliases too, so like R0 or Reg0 will work. And assemble, it puts the binary command sheet, put it in. It's in 16-bit form just because that's how the assembler takes it for their ROM modules. But again, you can do any value, any register. And then so I'll just move right out. So another thing I do is like for decreased RAM, that only requires one source target for like an ALU operation. Decrease just subtracts 1, and not pretty simple. So you don't really need to do a full 2. You shouldn't need to write a whole thing. So I have an alias pretty much for when you're decreasing RAM, it'll just say that RAM's the source and the target, and then it runs that operation on it and writes flags on normally. If you want it to not write flags, you do NF, but we'll keep that off for now. And then like doing an immediate to Reg 4 will determine where you do it, and then you can just do like branch always. So really simple program, just counting down from 200. Actually need to do 1 there. You can kind of see counting down here in RAM. So that's kind of how the assembler works. Pretty simple. Yeah. So I can kind of go more into the computer itself. All of these were made just from NAND gates and, well, tri-state buffers, which are the equivalent of just a transistor. And then, again, a normal NAND gate. I don't know. I mean, some of it's pretty nice. Like, this isn't too badly organized. the registers, and then this is coming from pretty basic like SR latch with turning into a D latch. I call it a DR latch because it has a reset option. That's actually really useful when I'm trying to reset it all. But I don't know, it's pretty normal computers too. And then, yeah, building the decoder didn't make me very happy, so that's not the most organized thing. But it works, and that's what really matters. It just kind of tells the entire computer what to do. And of course, made up of a bunch of other things, or stores the state that it's doing. So if you're doing an ALU operation or immediate, it'll remember that it's receiving a second byte for the command. But yeah, I try to optimize it as much as possible. I mean, all of the basic chips are just built from NAND gates. SRAM is built with mostly logic cells. This is actually pretty much just the design from Sebastian Legg's video. Very mess with the RAM, as you can see. And then these registers are kind of used in a lot of places. Pretty similar designs everywhere. Big thing here for the register file. This is flag register. It's pretty much the same thing, just with less logic. And the branch chip, depending on, it checks all of the flags and determines a whole ton of different things based off that, like 0, non-zero, equal, whatever. Yeah, there's a video decoder. This is determining what to do with the screen. It actually will display on the falling edge of the clock tick instead of the rising edge in like the entire of the computer. That's just because there's some timing issues with VRAM as they're all being sorted in the clock register for the address. So it needs to wait to the end of it to display properly. And then there's the program counter, basically just counting on itself. Reading to ROM, which is its own chip, I couldn't make that. But in real thing, you probably use some EEPROM or something. And there's a MUX. This is just for doing like physical instructions if I want to write the own by it myself, and then I can do a manual clock tick to input it. So just in the future, the plan is to be building Snake. We'll be starting with smaller programs like having a dot move around the screen and talking about more about my thought process behind everything. This is the original display of what I built, and then hopefully it'll build into something better.